this computer, and we're going to be off. All right, so we were talking about now the relationship between magnetic fields, changing magnetic fields specifically, changing magnetic fluxes. And remember, a flux is just a field times an area. And a changing magnetic flux gives us an electromotive force, a voltage, just like a battery does. And so that's the topic, and it's an important topic because previously we talked about electric fields separately, and the currents that got caused by electric potentials from electric fields and circuits and things like that. And then we started talking about magnetism, and there was a tie-in because currents caused magnetic fields. Wires with currents in them reacted to magnetic fields, and now we're definitely having a relationship between magnetic fields that are changing in time and electric fields that are then created, which cause electromotive forces, potentials. Oh, stop it, internet connection. My internet connection says it's unstable again. Haven't said anything overly important, just reviewing a little bit. And of course, those electric fields that are created from changing magnetic fields create electromotive forces, which create currents, which is kind of a novel idea and very practical because it allowed civilization, the civilized world, to develop a way to create electricity, create currents, and use it for useful things. Okay, anyway, we'll move on with that. Let me enable my pen here. And so it's kind of a 1, 2, 3 sort of process. When you're doing Faraday's law problems, the first thing you got to do is figure out, okay, what's the area through which the magnetic field is acting? And you look for a loop somewhere in a circuit. Okay, it happens to be this area right here, and that's why I said it's got a dimension L, and I just decided X would be this distance right here. Okay, that's X. All right, and so that's the area. The second thing you got to do is figure out what the flux is, and we're hoping that you don't have to do an integral over that area. That's not my intention. I don't think I have any problems where you really have to do an integral, but you have to recognize that the dot product is in there. You're hoping that the magnetic field and the area will be in the same direction, so you don't have to worry about the dot product, and you're hoping the magnetic field is constant over the area, so the integral of B dot dA is just B times A. And I'm being a little overly notationally exact by putting the magnitude of the magnetic field times the magnitude of the area. And then, of course, the last thing would be cosine of theta in order to pay homage to that dot product there. But in this case, they're perpendicular. The cosine of 90 degrees is 1. So it's just B times the area, which is B times L times X. Okay, so you got flux. The next thing is Faraday's law formally. Do a derivative. Don't take that negative sign too seriously. In fact, I'd almost say ignore it for now. Just get the magnitude of the electromotive force, the voltage, by taking the derivative. In this case, I recognize the magnetic field's constant. The length is constant. Hey, was I out the whole time? I just got an email or a little pop-up that says my internet connection's back. Lucky me. Thank you, Comcast. Anybody know what I pay for Comcast every month? It's ridiculous. I won't even admit to it. I'm almost embarrassed by how big a number I give to that company every year is. It's several $1,000s I give them every year. It's nutty, and this is what I get. But I suspect a lot of teachers right now are doing exactly what I'm doing. In any event, so you got the area. You found the magnetic flux.
Are you sharing your screen?
Say that again?
Are you sharing? Because I can't see it.
All right. Well, thank you. Apparently, I'm not. Let me make sure I am here. I thought I did, but it maybe didn't do it. So let's go share a screen, and let me clear these notes here real quick, just to so we'll start again maybe. All right. Where's the pointer? All right. I got a pen up. All right. Nothing's working here today. All right. Let's end the show, discard those, and start again. This time I'll make sure the share takes. I didn't look to see if it had the green, I get a green border when I'm sharing correctly. So let me go to it again. Share screen. There it is. All right, so we'll share. Definitely have a green border this time. Okay, and there you go. Come on, go full screen. Yep. All right, there we go. How's that? Better?
Yes, thank you.
All right, sorry about that. My obviously my mistake. All right, so anyway, we'll run through that real quick one more time. There's a 1, 2, 3 process here. Okay, and good to go with the pen. First thing you do is get the area, and the area is this area of the loop here that is being created. This was a problem we did at the end of class last time. I got this railroad track with a metal bar that's going to move. Okay, so there's the area I'm talking about. You see the length is given right there. I'm making that the distance x. Okay, so there's the area. Then you find the flux. Hopefully never have to do this integral, but you got to pay attention to that dot product. There's a cosine of theta in there, but in this case, the normal to that area and the magnetic field are in the same direction. So cosine of 0, what did I say before? Did I say cosine of 90 was 1 before? Boy, that would be bad. Cosine, oh, come on, internet connection. The cosine of 0 is 1. So I could ignore that guy right there. They're perpendicular to each other. Just B times A, right, is the flux of that loop. And of course, the area is L times X. Then the third step, you actually have to do a derivative here. Formally apply Faraday's law. I would ignore that negative sign for just a second. All right. And so I'm taking the rate of change of flux in time. Well, constant magnetic field, constant length right there. The only thing that's changing over time as you pull this bar to the right is x. So that's why I wrote dx dt right here. And of course, you remember from first semester, the derivative of position of an object with respect to time is its speed. I find that the electromotive force is the magnetic field times the length times the speed. Okay, this negative sign, we'll get that from Lenz's law. Lenz's law tells us that the current will flow, the electromotive force will be produced in such a way as to oppose the change which created it. Okay, but for now, if I want to find the current, I just take that voltage right there and divide by the resistance, Ohm's law, V equals IR. I just solve for the current by dividing through by the resistance. Remember, electromotive force is the same thing as voltage. It's just a term that has come into usage over the years for no real value, I think. I would have written it as V is equal to minus dB dt. I'm sorry, what was that? Pretty good? All right, anyway, so Lenz's law is the next question, I guess. What is the direction of this current? Since we are ignoring that negative sign, which way is the current going to go? And there really is only two choices, and that's what you're trying to figure out. It's either clockwise or it's counterclockwise. And I drew those backwards as I was saying it, clockwise or counterclockwise. It's one of those two, okay? And so which way is it? Well, if you look, the magnetic field is pointed right towards you out of the screen here. And so that would, in order to oppose that, I guess, I would have to create a magnetic field into the screen, and that magnetic field would be created by current swirling around clockwise. And so that's what I expect, not that. Okay. All right. So I think and oh yeah, yesterday we talked about motionally at MF. We realized that one side becomes positive and one side becomes negative. It's almost as if you got a little battery right there, and the current will go from the positive side around the resistor back to the negative side. So that's how linear generators work. It's kind of the nominal, important, simple to see Faraday's law problem. A lot of the others are a little more difficult to see. But I want to talk a little bit about power in this circuit. And I think if you remember from, I guess, last week, yeah, today's Wednesday already, we talked about the force on this bar being the current times its length times the magnetic field. Well, on the last slide, we just decided B times the length of the bar times its speed divided by R is the current, okay? And then I'm multiplying by the same length, and I'm multiplying by the same magnetic field again, right? And I'm using then the power equation that hopefully Professor Tech talked to you about. A force times a velocity gives you a mechanical power. And my point here, I guess, is while we pull this way with some velocity, that must mean that and that causes a force on this bar, which is in that direction. That's the direction of the magnetic force that I'm talking about here, okay? And so if I'm going to keep this thing moving at a constant velocity by Newton's first law, I better be applying a force in that direction that's exactly equal to the magnetic force, which is opposing it. All right. And so that's why I think the power that somebody has to put in would be the magnetic force times the velocity. Okay, they would, in order to just match these two things and move the bar at a constant velocity. In any event, just kind of multiply these two things out. You can see there's two magnetic fields squared. There's two lengths squared, velocity, two of those, velocity squared, all divided by the resistance. Now, in the other, and that's the power I think that somebody would have to put into this system to generate that current. Somebody would have to actually pull on this bar somehow to make it move with a constant velocity. And that's how big a force they would have to apply. And therefore, that's how much power they would be putting in, how much energy per time in watts. Unstable internet connection. All right, well, I'm going to continue on. On the other hand, you also should remember from chapter 28, I guess, where we talked about Kirchhoff's laws. Maybe I even introduced it in chapter 27. Electrical power that you get out would be equal to I squared R. I think you had to calculate that in one of the circuits labs as well. Okay, and so again, we'll take that same current that we finished up the last page with and found magnetic field squared, length squared, velocity squared over R squared is the value of current squared. And then I multiplied by the resistance, and that's the power I put in. And you should see one of those guys cancel. And the power electric that you get out, in this case, is exactly equal to the power that you put in. And so that's kind of reassuring, I guess. Now, in reality, you would expect that you wouldn't get as much power out as you put in, but I've ignored anything that might cause us to lose power right here. In reality, wouldn't there be a force of friction right there? Force of friction. And also probably right here would be a friction force. There might be air resistance. Okay, all of those would cause us to have to put a higher force on this bar that I've assumed right here. Okay, all of any friction, wind resistance, anything like that. And so the amount of power I put in, I would expect to be greater than the power I got out electrically, because I'm generating electricity. If I was able to get these to be the same, that would be a perfectly efficient generator. And that just doesn't exist because of real things. If I could make the friction as small as possible, I can certainly make the generation of the electrical power as efficient as I could. But this is an ideal case here on this slide. But it does make me reassured that the two results come out to be the same. All right. If we all of a sudden stopped putting that force in that was pulling the bar this way, well, I think there still would be the magnetic force that way as the bar as the bar was to move for us, right? There still would be a magnetic force back that way. And by the way, that's always a check on which way the current is going through this system, okay? Because I said before that I thought the current was going clockwise around this circuit, right? And so that means it must be going down in the bar. And so if I have a downward current and the magnetic field is coming out of the bar, out of the page towards me through the bar and through the loop, that must mean that the force is to the left, because that's the direction my thumb is going. And so that's always a check on your lens's law prediction, which way is the force. So anyway, if all of a sudden I stopped applying this force right here, what would happen to the bar? And hopefully you can see that the force, which is this guy, would be equal to the mass times the rate of change of velocity. And that rate of change I expect to be a slowing down. And I only show you this because it is an equation we've solved before. It has one derivative, okay? And I guess it has a velocity right here, and it has a whole bunch of constants right there. The magnetic field squared, the length of the bar squared, the mass of the bar, I guess, because that's what I used for MA, the resistance that's right here. And so the technique to solve this thing is what I called separation of variables. Okay, and that's what I did with the RC circuit, as you recall, and it's what I'm going to do on Monday next week when I put in something called an inductor in a circuit with a resistance. But it is true that dV here, dt, that's acceleration, right? dV dt, that's acceleration, is equal to minus the magnetic field squared, length squared, over mr times the velocity. And then the separation of variables part is I bring the velocity down to the denominator here and I bring the time over to there. So I'm left with dV over V is equal to minus that group of constants right there, B squared, L squared, magnetic field squared, length of the bar squared, over mass. And I have no idea why I wrote lowercase r. It's a resistor. It's got uppercase R is typically what we write. And then dt. And so I've separated in the sense that all the velocities are over here. The time and the constants are over there. And so my next step is to integrate both sides. If I integrate both sides, I get the natural log of the velocity is equal to those constants, B squared, L squared over mr times time. Okay, and to be fair here, I think what I did is I integrated from an initial time to a final time, and I had an initial velocity to a final velocity. Okay, the correspondence between the initial time when it was moving at some initial velocity and then what's going to happen to it over time. Well, let's see, this would be, well, that side, pretty trivial. T just goes in right there, 0 makes it 0. But this becomes the natural log of the velocity minus the natural log of the initial velocity. Difference of two logarithms is the ratio of those two things. So V over V0. Okay, and if I look at this piece right here, and I look at this piece right here, well, I exponentiate both sides because the exponent of a natural log just gives me V over V0 on the one side, and I'll write it right here next to the final result. And then I have to exponentiate the other side, and that makes it e to the minus all those constants times time, and I'm getting tired of writing those, so I'm just going to not write them right here. Okay, and then all I did is I slapped the initial velocity over the other side of the equation. So you can see what will happen. And I think this is one of the reasons why in an introductory physics course, this little piece of mathematics here that I did in 3 or 4 steps is an important piece, okay? And if you go on to take Dr. Hamilton's differential equations class, or perhaps some of you already have, this is one of the ones that you could solve as a result of just taking differential calculus, okay, with a little bit of integral calculus, I guess. You have to know that the integral of dv over v is a natural log, but otherwise it's a pretty straightforward thing to do. It's the perhaps most important but simplest differential equation in nature, because it tells us the bar's just not going to like grind to a screeching halt. What the bar will do over time, if you look at its velocity, is start at some initial value and it'll exponentially decay over time. And that's often how nature works. It's just one more example. Just as the current decayed exponentially in an RC circuit, radioactivity decays exponentially. I'm sure you can think of other science examples. This is an important one. All right, so that's what happens if you take the force away. The bar will coast to a stop with an exponential decay. And of course, the bigger the magnetic field is, the longer the bar, well, the faster that'll happen. All right, another important application of this, I think, is a rotating generator. And this is a clever idea that somebody thought. Unfortunately, we got those brushes to deal with again. They're called slip rings. In this case, you notice this is a continuous loop, and that's a continuous loop. It's on this axle that is somehow caused to rotate. And you know, how do we do that? Well, initially it was water power in this country. Okay, a lot of this went on in places like Niagara Falls, other places where the water changed height, and you can use it to turn some sort of paddle wheel or a turbine. In a lot of engine applications, steam is what's used. We heat up water to make high energy steam. We run steam through a steam turbine, and that could make this thing turn. With jet engines out there now, gas turbines are the way you could make this axle rotate. You can hook it up to an engine with pistons, either a diesel or a gas engine, and you can make it turn around just like your car axles do. Somehow you got to make this axle rotate, okay? And you put a loop of wire. We just shown one here. Obviously, it's many, many, many loops in a series configuration around there. And then at the very end here, you get you get the power out that you need, okay? And so what happens, I guess, same steps we talked about before. What area do we have? And it's right there, right? I'm looking at this loop, and you can't see the backside, but it's sitting there in between the poles of a permanent magnet. And so the flux must just be B times A. But now if you look, that's the direction normal to the loop, and the magnetic field is right there. And so I've got this angle theta between those two, and that's what I'm talking about right here. Now, there will be a place where the cosine will be 0, and that'll be 1 when the two are lined up. It's similar to the worksheet problem that you had the other day, right? And then there's also a place where this will be 90 degrees, cosine of 90 degrees is 0, and then at that point the flux will be 0. So clearly, as this thing is forced to rotate around by some engine of some sort that is making it rotate, the magnetic flux is going to change because of the rotation, okay? Because this, by virtue of the fact that this angle is forced to change. Well, I'm hoping that you remember from first semester, in a constant angular velocity problem, and that's what we're assuming, it's moving at a constant angular velocity. Theta is equal to theta initial plus omega t plus 1/2, and now this is the angular acceleration, alpha times t squared. But I'm going to assume that we don't have any angular acceleration. We don't have any initial place. We'll just start at the initial angle being 0. And so theta here just changes as the angular velocity, omega, times time. Okay? And that is what the magnetic flux is doing. Faraday's law, formally applied. These are kind of my steps from before. I guess area, right? Flux. And now the rate of change of flux in time is Faraday's law formally applied. I'm going to make use of this negative sign here, but my advice is only think about this as magnitude. Okay, so I've got this guy right here that I have to take the time derivative of. Magnetic field's a constant. That area is a constant once I build this loop. Okay, so I take the derivative of cosine. The derivative of the cosine is minus the sine, and that neatly makes that negative sign go away, but I'm still thinking about magnitudes anyway. And so what it looks like to me is the electromotive force that's going to come out at these rings right here, because this one is attached to that ring, and this one right here kind of goes right on the inside of it and is attached to there. So the electromotive force between the points A and C is going to change over time like a sine wave, right? It'll have some maximum value, go to 0, some minimum value, go to 0, max, and we call that alternating voltage, really. We refer to it as alternating current, AC, because if I divide it through by some resistance of maybe this light bulb over here, I could divide by resistance and get current. And so we refer to this as alternating current. So rotating generators of this sort, following Faraday's law, make alternating current, alternating voltage that looks just like that as a function of time. Okay, as I said, one loop here would be a pretty inefficient generator. So typically, thousands of loops spooled around like thread on this axle right here, on this drum. Okay, and so that would be the electromotive force. I always find, especially now with no basketball going, this is kind of an easy equation for me to remember. It's NBA times omega. Okay, the angular speed of this thing in radians per second. Don't go degrees per second, radians per second. And that'll get me an electromotive force. Magnetic field times an area times a radian per second, sure enough, gets me a volt. All right, in most cases, as I said, you just don't have one loop. You do something like this. Different designs of these things. In my case, I guess This is one way I can put more loops in between a magnetic field. The magnetic field doesn't have to be a ferromagnetic piece of metal. You can bring in some current to just create a stationary magnetic field if you want. And then people decided, well, I just don't need two poles, a north and a south. I can have a whole bunch of poles, and as they rotate around, they'll change the flux a whole lot quicker, won't they? It'll be changing faster. If the flux changes faster, you can get a higher voltage produced. And so those are some cross sections of real looking rotating generators. I do want to make an interesting kind of observation. In electric cars right now, there's the fact that you can generate currents in these loops of wires is used to actually brake the car without brake pads. So you don't actually have to have contact. You just have to bring a magnet nearby. And so there is a little kind of a device called an eddy current braking device. And it uses the same idea of generating loops of current like a generator does, except it's in a solid piece of metal, which is fairly strange. And so let's say this disc right here and make it aluminum. If you've ever looked behind your tire on your car, you'll see that there is a metal disc. Internet connection is unstable. And then the way most cars stop is there's this like a caliper on a bicycle that squeezes this thing with a piece of rubber from both sides, and that causes the disc to slow down. And usually you have that on all four tires. There's another design where it's kind of a drum, and it presses the rubber that makes the friction cause the car to come to stop comes in from the outside. It gets pressed that way, or sometimes from the inside even. Okay, so in any event, hopefully I'm back here. This thing is rotating around, and I guess a piece of metal right here is about to come in where there's a magnetic field into the page, okay? And then that same piece of metal will continue to rotate right to there, and will continue to rotate there. So I kind of have three places right here where this hunk of metal right here is rotating through a magnetic field. And if you notice, there is no magnetic field right here. None, zero. So we can ignore that. As it moves over here, all of a sudden there is a magnetic field that the piece of metal senses that is into the screen. And so a current will flow to oppose that. Well, let's see, that means I need a magnetic field out of the screen. And so as this piece comes into this region right here, it will start to make current loops that are in that direction. Okay, with being the strongest right there as it's coming in, okay? And so that's what's gonna happen to that piece of wire. On the other hand, as it recedes, okay, eventually the magnetic field is constant as seen by that hunk of metal, okay? So constant right there, not changing. And then as it goes out the other side, now it had a magnetic field and all of a sudden it's not. It's going to try to create a little magnetic field in that piece of metal. So current is going to run around clockwise to try to recreate the magnetic field into the page. Now, Faraday's law is a losing law because it can never create the full magnetic field, but current will flow in this direction in order to try to create that as that piece of metal recedes from that point. Okay, so let's look at what happens to this now using our force law, IL cross B. And hopefully you can see that over here on the left, where as I said, it's trying to oppose this change in field into the page, so it's having counterclockwise currents. And over here on the other side, where it's trying to recreate the magnetic field it was just experiencing, that's the little piece of metal of the disc, current starts swirling around clockwise. Look what happens right here. I got current going up right here. I got magnetic field into the page, creates a force to the left, okay, opposing this rotation. And same things I think happening over here as it recedes, current up, magnetic field into the page, forces to the left. So both of these changes of a magnetic field as seen by this metal disc cause a force which is tending to slow down the rotation. And we call that dynamic braking. All right, so all you have to do there then, instead of bringing a magnetic field, instead of bringing a set of rubber calipers to squeeze on this thing and cause it to slow down by friction, all you have to do is bring a magnet close to the rotating disc, and it'll tend to slow it down without any contact. One of the pieces of maintenance you find you have to do on your car is to replace those pieces of rubber that are slowing down the metal disc here. Well, all of a sudden with a magnet, you don't need that anymore. You have no need to actually have contact. There's no disc that gets worn away. There's no piece of rubber that gets worn away, and so it's a much more efficient system. And the clever engineers who work for Tesla and other places like that are even trying to work on ways to capture some of this current which is swirling around here in these discs and use it to charge the battery of the electric car. So every time you step on the brakes, you're actually generating electricity. You just have to change the design from a simple disc. In any event, eddy currents. I do have a point there, though. I've got current which is being generated just in a piece of metal, okay? It's not actually going through a wire like in the generator. And so that implies if there's current just moving around in a piece of metal, there must be some electric field that's causing the current to go around in that piece of metal. And so I want to go back and think about, oh, that's supposed to be a circle, isn't it? I want to go back and think about a circle here. We talked about unstable internet connection. We talked about the definition of electric potential being an electric field integrated over a length. And we said most often that'll be a nice simple equation. You even saw it on the exam yesterday, something like this, right? The voltage is equal to an electric field times a distance. If the electric field is constant, it just becomes that. All right. But in these eddy currents that I'm talking about, apparently, if the current is being made to go around in a circle, apparently it's just not E times D, it's E dot DL around a closed loop. And that must be the voltage, which we call the electromotive force. Okay, and so I've just taken this and I've made these little circular paths where current was flowing, right? That's what I was drawing right there. And so I've got the integral of E dot DL is the electromotive force causing that current to go around. And that must be, according to Faraday's law, the rate of change of the magnetic flux that's being seen. Okay, and so we've put two laws together right here. In Faraday's law, and you can see right away that changing a magnetic flux doesn't just create an electromotive force. It also must create an electric field that is also circulating around like this, and that must be what's causing the current, causing the charges to move. All right. Yeah, this isn't looking good. Hopefully it does better on the PowerPoint I saved in Canvas. Any event, this is what Faraday's law boils down to. Changing a magnetic flux causes an electric field, and changing that magnetic flux in a uniform way will cause a circular electric field. And here's the picture, I guess, where all of these my equation program didn't do well here. Here's kind of the picture. Just like when we did Ampere's law, which was B dot DL over a closed path, we always wanted it to become the magnetic field times the circumference. Same thing here. We think these are little loops, and so we're going to use 2 times pi times r for the integral of DL around a closed path. We're making the assumption, and it's a good one from symmetry, that the electric field is the same everywhere around that path. All right, so that's that side of Faraday's law using this new idea. We did just like we did with Ampere's law, only we've changed the field from a magnetic field to an electric field over here, and we're finding the rate of change of the flux. Well, the flux would just be the magnetic field times the area. The area is a constant. I'm assuming at a particular place, R is a constant. Okay, that's why I drew a circular loop around here to do this side to get the circumference. It's also, I'm going to use that area. That's the area which is bounded by that little circular loop. And that's where the magnetic field is changing. That's where the magnetic flux is changing. And so if I look at this, I see, that cancels. And if I want to find how big the electric field is, which actually caused current to move in a circle in, say, a piece of metal, if it was there, it's just the radius I'm at divided by 2. And it would be the rate of change of the magnetic field in time. So a changing magnetic field in time creates an electric field. And, Faraday was, I said the other day, more of an experimental guy. He had no theoretical training in high-level math or physics, but he did make these observations. That's arguably one of the most important observations of the 1800s, is that I can change a magnetic field and create an electric field. And we're going to show here in a bit, be next week sometime, that if we change an electric field, we could create a magnetic field. An important idea, because that ultimately is how we figure electromagnetic radiation moves through free space. We create a changing electric field, that creates a magnetic field. It's probably going to be changing. The magnetic field is going to be changing, that creates an electric field, which will be changing. And those two will bounce off of each other. And through free space, we can move these electric and magnetic fields, which are always changing. We call that electromagnetic radiation. It's radar, it's AM radio, it's FM radio, it's the microwaves that heat up your food, it's light, because light is just a special frequency band of the electromagnetic radiation spectrum. And so a very profound idea. I would point out, what if you were outside of this? What would be the electric field out here? It's pretty much the same problem. Okay, I've just made R bigger, but of course this guy right here would become the radius where the magnetic field is. So it wouldn't cancel right here. I guess I'd have R0 squared, and then I divide by 2R. So outside of this area, I think the electric field would be decaying away as 1 over R. And that's it. All right, I think I'm done for today with new material. I'll hold on for a second for questions. And if not, we're going to look at some Faraday's law, Lenz's law examples, and we'll use iClicker Reef, I guess. All right, so I want to escape. Don't keep my annotations. And so if you go to iClicker Reef right now, hopefully you'll find, if I make this a little smaller, let me log into iClicker Reef here. Any questions while we're transitioning over here? Let's back up to, all right, I'm logging into me. Join. I'm checked in. Hopefully you are here as well. And I'll be able to participate here in a second. And this first question I have for you has to do with magnetic flux. And so let's make the screen work a little bigger here. Make that smaller. There's even a way to get this to go away. I just don't know how. And I think I'm sharing the wrong thing. So I'm going to stop share here. And I'm going to share the other screen with you. Yeah, there it is. Share that screen. All right. While I transitioned over, hopefully you're seeing, do I see, yep, I see the green border around it. In Zoom, you're seeing this question where the loop is in the plane of the paper and the field is perpendicular to the paper. And the question is, what is the magnetic flux? So go ahead and give me an answer here. Now. Okay, I see it. And I want, I'm in. 2, okay, somebody else is out there, good. And while you're doing that, I'm going to grab a little bit of people are still left despite the bad internet connection I had. All right, 7. All right, I see 13 of 19 are still here with us in the Zoom session. And if you look, I've got a quorum here of responses. It says it's the first one. Pretty straightforward question, I hope. So let's call it a day on this one. And sure enough, oops, I don't want to do that. I got to keep this over here. I think just a magnetic field times pi r squared. The only issue would be if there was some angle between the magnetic field and the normal to that loop. That'd be about it. All right, let's move on to the next one. All right, so here's a question, I guess. What's the magnetic flux this time? And go for it. All right, didn't go on here. Well, somebody's in. I don't see it on mine. So let's go back. That one, I guess. No response. Huh. Seven people are in. 8, 9, 10. Oh, look at that. Must have taken a second for everybody to get their iClicker going. 12 responses. Good. And let's look at the graph here, because that may be about everybody. And we're kind of stuck between C and D. And you know, I have to warn you, in any physics problem, the angle that you're given might not be the best angle that you want. Okay, because in the equation for flux, and let me put this away for just a second. We'll call a day on that, and we'll come on over to, nope, I can't do that. I got to keep it over here somewhere. I need to, of course, I put it right on top of my toolbar. Move. No, don't stop. No, do not end. I need the annotate bars. I've got two toolbars going here, and I need to, there it is. I move it that way. Come back over here. I want to annotate, draw. Think about where the normal to this plane is, and I'll draw it right here. It's right there, right? And it's right there. And when we say flux is equal to B times A times the cosine of theta, okay, it's not this angle right here. It's that angle right there that is the theta. That's the angle in between A and B, the normal to the area and the magnetic field, not with respect to the surface itself, that. And so if this is a 60-degree angle, this is a 30-degree angle. And so actually, the answer would be that guy right there. It would be D. Okay, so just be careful. It's sort of like you often get a diameter, and the equation needs a radius, so you got to divide it by 2 to get a radius, and people forget to do that. If you're given an angle, make sure it's the right angle that is needed for either the dot product or the cross product, the one that's in between the two vectors right here. Okay, and conceptually, you'll use the wrong angle, and you kind of got the right idea. It was an attention to detail issue of making sure that the angle is the correct one. All right, let's move on. I guess I have to turn off I need my mouse back. Then I can hit to the next slide here. I want to erase all this stuff though. Go away, go away, go away, go away. And now this is an interesting problem. See the loop here that is being formed? I see it as sort of a piece of paper folded over the top, but I guess it's an optical illusion. You could see it as a piece of paper this way as well. But in fact, the point is the magnetic field is going to the right, and this oddly shaped area here, what's the magnetic flux going through it? And I got to hit that start key, don't I? There we go. So sorry about that. I was a little slow. And what do I want? I'm in and somebody else is in, apparently.
Can you explain what that shape is again? You cut out.
Now, sure. Let me, if you can see my picture, I'll try to draw it. But I see it two ways, and either one should get you the same answer. In one case, it's folded sort of like this, right? I can see that. And then in the other case, I can see it folded like this.
Okay.
But it's still an area. And so there's 3 segments to it. Let's draw right here. I guess if you see it in one particular configuration, there's an area right here. There's an area right here.
Okay.
And then there's an area down at the bottom. Okay. Another way you can see it is there's an area at front, area at the back, area at the top. The question still is, what's the magnetic flux? And I think you have to, no matter which way you see this, you get the same answer for what the magnetic flux is.
Okay. Thank you.
You bet. All right, looks like what I got about 8 people in. Actually, I'll put those back. All right, looks like we got a quorum in, 12 people are in. I'm going to do the easy one first, because you could see it in 2 different ways. It's kind of like one of those cubes people draw. It's a cube going towards you, away from you. And I'm going to go with the one where there's an area out front here, and then there's an area in the back here, and then there's this area on the top, okay? And so I think if you look, the area in the front, the area in the back, the magnetic field and the normal to those areas, 90 degrees. Cosine of 90 degrees is 0. Up on the top here, the normal is outward, okay? And again, that 0 flux. I think that's the easy one, all right? If you see this piece of this loop here slightly different, you'll see that, okay, there's an area over here on the side. Okay, and I would have the area go that way to be consistent with an area on this side. And of course, down here, there's an area on the bottom. And I've always had the area pointing in the same direction. Well, at the bottom, I think clearly 90 degrees, 0 right there. Over here, I got 180 degrees. Cosine of 180 degrees is -1. Over here, I got 0. Cosine of 0 is +1. So if you see it this way, you might see a negative flux on this side, and the negative flux would be the area C times A times the magnetic field strength. So on this side, it would be minus C, I said C times A, C times B, okay, the area of that thing, times the magnetic field, and it's minus because the normal is that way, and the magnetic field is the opposite direction. On this side, they're both in the same direction, same dimensions though, C times B times B. And so on this side, it's plus because the normal is that way and in the same direction as the magnetic field. And so I think you'd see those two add up to be 0. So in either case, the answer is 0. How'd we do on that one? I didn't look. Yeah, so the 5 of you that said 0, I think you got it here. And either way, that's what the answer is. So let's put this away. Get rid of that, and let's go on to the next one. Got to do that. Let me erase my etchings here. All right, so those were just, I got one more, I think, on identifying fluxes, because that is the first step of Ampere's law. I'm sorry, of Faraday's law. Let's talk about this one now. Okay, so now the field is oriented downward. That same loop, okay, and you can see it either way here. What is the flux through that guy? And I'll get rid of my little etchings right here. All right. And I'll look at, okay, right here, I kind of see that as one area here, okay? And then I see this one as an area. But that's not really playing because there's the normal on that side. There's the normal on that side. That's just enough of a hint for you, I guess. This dimension right here would be C, I guess, since it's the same dimension as that one. Of course, the other dimension is right there. All right, so we'll stop that right there. And I think, let's see what people, a majority view seems to be D, which I would agree with, because regardless of how you see this, this loop here, The area that matters is either the bottom loop, I suspect some of you see that, or some of you may see it as the top part of the loop right here. Both of those have area. Let's see, the area would be C times A, right? Or AC, maybe written in alphabetical order. That's what the area is on either the top or the bottom that the magnetic field is going through, okay? So I think then the magnetic field times the area would be the right answer. And so that's why D carries the day here. All right, get rid of all this. You know, there's actually a clear all drawings. There we go. And then I can get my mouse back, go on over to the next one. All right, and here's kind of the classic problem we have with this. And let's close that up. So I've got the south pole of a magnet coming into a bunch of loops. And the question is, in the resistor here, is the current going to the left or is the current going to the right? And so let's see. Boom. All right, I got it. And nobody's in yet. You're all thinking it through. This will probably be the last one, and I got to let you go here. All right, think about the original magnetic field, which direction it's in. And the original magnetic field would probably be like that. That's the initial. And then as you move the magnet that way, it becomes bigger. So that's a later time. I'll call that final. So the change in the magnetic field is that way, right? That's how the magnetic field changes. Lenz's law says you're going to create a current that opposes that. So the current is going to create a magnetic field. And by the way, both these magnetic fields should be inside. It was just getting a little crowded in there. That's the direction of the induced magnetic field that opposes the change. See, the change was that way. That's the direction that Faraday's law and Lenz's law say the magnetic field is going to be created. And so how will current flow in order to create a magnetic field in that direction? All right. I got about 10 in. Let's call it quits right there because I got to let you go here. I think the answer is if I need to create a magnetic field to the right to oppose a change that's to the left, and this is, you're using two right-hand rules here, I guess, that must mean that there's a current going that way over each of these loops, going around that way. That will create a magnetic field in that direction. When you get to the last loop here, it goes that way through the resistor. So I think the answer is A, to the left. All right. Hey, I got to let you go here. We've been going long enough. We'll do a couple more of these on Friday. Great job to all the people who got a nice A or above. For those of you that didn't quite get that, I'll look and see. Professor Tech in the past had done some kind of remediation where I put out some problems again, and you can buy back. I was told he gave you 10% back on a problem you missed if you correct it. And you know, we'll see if there's some sort of system like that we need. Otherwise, you all have a great day. We'll see you on Friday. I'll stop sharing this. I will have longer. We'll have a office hours set up for you all later on today. So stop recording here. 1 o'clock. Actually, I may go 1:30 again.